In section 3.6, we're going to look at continuous growth and decay models. So they're going to be similar to the continuous interest situations that we looked at in 3.5. We're going to do some problem solving with continuous growth and decay models. We're going to discover the relationships between the exponential functions defined by y equals ab to the t and those defined by y equals ae to the kt, the annual growth style and the continuous growth style. We're going to solve problems involving continuous growth and decay models. We're going to graph those e-based exponential functions. We're going to talk about the domain and the range of all of our exponential functions as well. So in our first scenario here, we're talking about the US population in 2016 compared to the population in 2017. So we're going to let our time be measured in years since 2016. So 2016 is year 0. And so our initial value A is going to be the population in 2016. So our A value is going to be 323,756,681. Okay, then the annual growth factor B can be found by computing the ratio of 2 consecutive years output. So I can compute B with the ratio dividing these two values. With the second y value on top and the first y value on the bottom. So y2 divided by y1. And we need to compute this ratio here. So that gives us 1.0068. I want to make sure that I don't round this too soon. I'm going to keep 4 places on this because otherwise, 1 obviously would not be an appropriate base because that would show no growth at all, and there has been growth. If I round it to 1.007, 3 places would be my minimum I ever want for a base, but 4 is a decent number of places. Sometimes we might even want more, but I'm going to keep 4 places right here to start for our base. The more places we have in the base, since the base is the part that gets repeated, the better our model is going to be. If we have more error in the base, that error is going to be compounded more frequently and we'll have more error in our results. So the more places, the better. Minimum here, right, 4 for this particular value, especially with those 2 zeros here. You need to have a couple places that are significant figures. All right, so what is the annual growth rate? So my growth factor, B, is 1.0068. And so the growth rate, if I subtract the 1 and move the decimal place, would be 0.68%. Subtract the 1, it's 0.0068. Move it twice to make it into a percentage. So 0.68% is the growth rate. All right, and the equation for this, I'll make it in function notation, P of t. It's going to have our A value times our B to the t. Okay, so the population did not remain constant and suddenly increase, so it grew continuously. This exponential model, the exponential function used to model continuous growth is the same type to model continuous compounding for an investment. So we're going to be working on this type of model, continuous compounding, the A equals P times e to the RT that we saw in the last section. We're just going to change the names of some of the variables. In this particular case, when we saw it in section 3.5, the P stood for principal, R stood for interest rate. We're going to generalize that. So A is just the initial value, like it had been up here. A is the initial value. It was called P when it was the principal, which was the initial investment, but that letter P stands specifically in the monetary case. So we're going to generalize it and just call it A. And then e to the KT, it's not always an interest rate, so we're not going to call it R, but we're going to use K to be the continuous growth rate, A to be the initial value, and then Y as our output. And of course, T is still time. Okay. And E is still Euler's number, the 2.7182848, and so on. All right. So noting here that if these two equations make the same model, if the y equals a times b to the t and y equals a times e to the kt, if those two equations are going to be used on the same data set, the same model, then they must be equal to each other. And because a is already equal to a, it means that b to the t must be equal to e to the kt. So if b to the t is equal to e to the kt, again, those both have t, so it must mean that b is equal to e to the k. So that's what we're going to notice about the relationship right here. If these are going to be equal, the a's are already the same, they already have t as the power, so the base b has got to be equal to e to the k. All right. Now, here they did round their b, it looks like, to 1.007. I had kept it as 1.0068. We can use either value here. I'll go ahead with the 1.007 since that's the way they've got it rounded here. That's going to be our b value. So we'll plug this in here for b. So we'll have our 1.007 equals e to the k, and we're going to solve for k. Now, we're going to solve for k graphically by graphing y equals 1.007 and graphing y equals e to the k. So we can find out where our intersection is. We can find the ordered pair where we have the k value discovered. So let's go ahead and get that started. We want to find out where 1.007 is equal to e to the k. And I have to be careful because it looks like it's almost hitting on the the y-axis here. Almost looks like it's hitting at 0, 1. But if I zoom in quite a bit, I will see that the intersection point is not on 0, 1. It's over here at 0.00698, comma, of course, the 1.007, which I set it equal to. Okay, so this means that k is 0.00698, or if I move the decimal place twice, it would be 0.698%. So just want to note that the value for k, the continuous rate, the continuous growth rate, is not the same, but is close to the annual growth rate R that we saw above, the 0.68 compared to the 0.698. It's not a large difference. One of the reasons that we need to make sure that we're keeping several decimal places as we make our predictions here, or it might come out that they look very similar. They need to stay separate, so we need to make sure we keep many places. I probably would have kept an additional place here myself. If they had not told me to round to 7, I would have kept this as 6, 8 here. That would have changed the value slightly, and it actually would have made it a little smaller. It would have made it 0.678. The numbers are still going to be different from each other. Again, just for comparison, we might have had, again, a different number based on how we round it. So we got to pay attention to the way that the question's asking us to round it. But the more places that I include, the more accurate the prediction is going to be. So I'm going to rewrite this function now in continuous growth form. So in continuous growth form, the a value is going to stay the same. So I'm still going to have p of t equals 323,756,681. But now it's going to be times e, the base of the continuous growth function, to the k, which is 0.00698 t. So this is going to be in continuous growth form. Okay. So they want us to notice that the annual growth rate R of 0.7%, or R's we had not rounded as soon, so we said 0.68%, is equivalent to the continuous growth rate of 0.698%. And so again, we can see that those are not equal. The annual growth rate is R, annual growth rate R, compared to the continuous growth rate K. All right, so let's read our definition box here. An exponential model used to describe continuous growth at a constant percentage rate is y equals a e to the k, where k is the constant continuous growth rate and a is the amount present initially. So k is the constant continuous growth rate, a is the amount present initially when time is 0, and e is just that irrational number approximately equal to 2.7184828 and so on. 2.7182848, I believe. I flipped those numbers. But it is a constant used by the letter E. Okay, so there's another example here of taking a function that's in annual growth form and changing it into continuous growth form by setting the base equal to e to the k, and then you have to graph both sides to figure out what the k value is. You can check this one and determine the value for k as you see here. Now, we're going to look at the next situation. We're going to consider a situation that involves continuous decay at a constant percentage rate. So Tylenol or acetaminophen is metabolized in your body and eliminated at a rate of 24% per hour. We're going to take 2 Tylenol tablets, 2 500 milligram tablets, I assume, because the total is going to be 1,000 milligrams by noon. Now, I do say annual a lot when I talk about the y equals AB to the t model, but annual is if the assumption is that the time unit is in years. It also could be hourly. This one's going to be hourly for our AB to the t model. It's the units on the time, or whatever the units are on the input time. So in the previous case, it was an annual growth rate for our R. Our R in this case is going to be an hourly growth rate because those are the time units in this situation. We say annual frequently because frequently the input for time is in years, but it is not always, and it does not necessarily need to be in years. So we're going to start by writing the hourly model, the time-based model, the hourly model with AB to the t, and the initial value A for this situation would be 1,000 because you take 1,000 milligrams initially. And then the decay factor, remembering that for the decay factor, you're going to find out how far below 1 you go if you're decaying at a rate of 24% per hour. So 1 minus 0.24, and that gives us, if we take that difference, 1 minus 0.24 gives us 0.76. So that is going to be our decay factor, our hourly decay factor. I'll make us also note about this as well. This is our hourly decay factor. And I can put these together to write the exponential function. And they want us to call it Q, it looks like. So Q of t equals 1,000 times 0.76 to the t. All right. Now, of course, the amount of Tylenol does not suddenly decrease by 24% at the end of the hour. So we're going to want to rewrite this in continuous format, just so that we can discuss what the continual decay rate is as compared to the hourly decay rate of 24%. Okay, so again, we've already established that B is equal to e to the k. We're going to take that on to the next page here. So our B value of 0.76 is equal to e to the k. We're going to graph both sides of this. We're going to graph y equals 0.76. We're going to graph y equals e to the k. All right, I already have e to the k graphed here. So let's just go ahead and graph y equals 0.76. I'm going to need to zoom out a little bit. And again, if you were in a standard window, you'd be zooming in to find this value. So it turns out from graphing when we find our intersection point right there, that our k value is negative 0.2744. Okay, so if I write this function now in continuous form, it's going to be q of t equals the a value is still 1,000. Instead of 0.76 to the t, we're going to have e to the negative 0.2744 t. So the values that we're comparing that are close to each other are not the 0.76 and the 27.44. Remember that 0.76, that is the decay factor. We want to compare that to R, which was 24, I forgot, 24%, I believe. And so this one right here is showing a decrease continuously of 27.4%. So 27%, obviously we're not comparing the decimal to the percentage, but 0.27 to 0.24 or 27% to 24%. Okay. Now, other notes right here. If our B value is less than 1, then we know that we're decaying, right? In this case, our K value is going to be less than 0 to show that we're decaying. K value is less than 0 to show that we're decaying. So it's a negative value for K to show that we're decaying versus if it had been in the hourly form, it would have just been a number less than 0, though still positive for the decay factor. Okay, so in our box here, for exponential decrease, in the model y equals ae to the kt, the k value is less than 0, and the absolute value of k, which would have been 27.4% right here, is the continuous decrease. A, of course, is the initial amount present, and e is that irrational constant. All right, so there's another example in example 2 of them working through the same thing. You can double check. You can do your a equals e to the k, you can graph it, you can find your k, and you can find your percent decay for the continuous model. All right, looking down at number 5, we're going to switch gears and look at the graphs of exponential functions having base e. So first, we just want to consider the graph of y equals e to the x. So I already have that graphed up here. I can change the letter k to x, although it doesn't really matter what I call the variable. It's the same graph. And I'm going to zoom home on that. And it's the shape of any exponential function we've seen before. It's just the base is not a rational number. That's all right. I'm gonna go ahead and make it not y, but f of x, because I can see that I'm gonna have a table to do down here. So what's the domain? So the domain is the set of inputs, and you can see that you go left, you go right, you're gonna have all real numbers, just like every single one of our exponential functions, all real numbers for its domain. Is it increasing or decreasing? It's increasing. And that's because the base, e, is greater than 1. E approximates as 2.7 something something, and that's larger than 1, so it's an increasing exponential function. Now, let's get our table started here, and we'll do our autofill for f of x1 and our inputs of -3, oops, I didn't hit enter apparently, and all the way up through 5. Okay. So it says round to 2 places if necessary. It's going to be necessary in almost all of these cases. So we're going to say 0.05, 0.14, 0.37. Anything to the 0 power is 1, including e to the 0 is 1. Then we'll have 2.72, 7.39, and so on, 20.09, 54.60, and 148.41. And again, rounding to 2 places, we had to take the third place and round up if necessary. All right, sketch the graph. Okay. I can see it, so I'm just going to draw something similar to what I see. Desmos is really helping us see the graph, but this is my approximation of what it looks like. So slow growth followed by rapid growth, the shape of any exponential function. What's the horizontal asymptote? Well, these values over here are getting close to y equals 0, just like the majority of our other exponential functions with bases of other things, like 2 or 1/5 or whatever it was. What is the range? Very similar to the other ones. This has a range from 0 to infinity. 0 is our low border for height. Does not hit, does not go below. So parentheses on that 0 because it's not hit it. Goes up to infinity. What are the intercepts? There is a y-intercept at 0, 1. This would be our 0, 1. And there is no x-intercept because it does not come down and hit the x-axis. Is the function continuous over its domain? Yes, continuous means connected. So it's not discrete, which would be a set of isolated dots, right? It's continuous, it's connected. Okay, so that ends the first example. Then in number 6, we're going to look at vertical shift. A vertical shift of this graph will change the horizontal asymptote. So we're going to look at the vertical shift that takes y equal to e to the x plus 2, then we're going to take y equals e to the x minus 2. We're going to look at how that changes the horizontal asymptote. So I'm actually going to turn my table off, or I could get rid of it. I don't need it anymore. Let's go ahead and get rid of it. And I'm going to draw in the asymptote right here, y equals 0, and I'll go ahead and dash it. And we're going to see that when we change this function to add the 2 to it, this is no longer the bottom border. If I had y equals 0, I'd have to add that 2 to it as well, move that up, and that's going to be our new border. So the border used to be at 0, but since I've added 2 to the function, now the bottom border is at 2. So y equals 2 is the horizontal asymptote here. Now, if I instead subtracted 2, that lowers the function by 2, and so down here at -2, that's going to be our border. So we've lowered it down to -2. You can see that's the bottom border of the function. So here you can see that the horizontal asymptote is y equals -2. So we've shifted the function up by 2, so we also shift the asymptote up by 2. We shifted the function down by 2, so we've also shifted the asymptote down by 2. That's all I need for the graph for the moment. Let's take a look at the bottom. Identify the given exponential function if it's increasing or decreasing. In each case, give the initial value and the rate of increase or decrease. Okay, so the initial value, I'll just list that as A, is 2,500 or 2,500 for the first one. And then this is an increasing exponential function. So it has a continual growth or decay rate. So the continual growth or decay rate, 0.4, corresponds as 4%. So we are going to change that. We can write 0.4 first, but all rates, whether they're R values or K values, should be expressed in percent. So it's a 4%, and it wants us to identify if it's increase or decrease. So it's a 4% increase. K values are increase if they are positive and decrease if they are negative. So we've got a 4% increase, 4% continual increase. So let me put the word continuous in there. But since it's K, continuous should be implied for this rate, but it doesn't hurt to say 4% continuous increase. Okay, then in the next function, the A value is 400. It's still, our initial value is still found as the coefficient. Now, I don't know the initial, I don't know the rate of increase yet, but what I do see, first of all, rate of increase or decrease, is the growth or decay factor. And the growth or decay factor is a 0.86. That's going to allow me to determine the R value. I don't know it yet. Because that is less than 1, B is a decay factor. So if I wanted to find R, I'm going to take 1 minus 0.86. And that gives us 0.14, which is 14%. So what we have here for R is we have a 14%, and I don't know if it's annual or hourly or whatever, but annual is the general assumption. So we'll go ahead and put that word here, annual decrease. Okay. Could be hourly. I don't have a situation to know what the time base is, but it's time-based decrease, not continuous. All right, in the next one, we have our A value is 75, and inside of our function, we have a growth factor of 1.032. So this means I can compute the growth rate with 1.032 minus 1, that's 0.032, or move it twice, that would be 3.2%. So that is a 3.2% annual increase. Remember, I knew that I was decreasing in part B because the factor, the decay factor, is a base less than 1. So I see that I'm decreasing if the base is less than 1. So when I compute the decay rate, I subtract it from 1. And because this base was larger than 1, I knew that that was a growth factor. And so my rate was going to be a growth rate or a rate of increase. And last, the A value, the initial value here is 12. The K value is negative 0.12. So that means a 12% continuous decrease. It's a decrease because of the negative. I don't say the negative when I write the sentence about decrease. Remember, it's the absolute value of K here, or the decrease gets absorbed, the negative gets absorbed in the word decrease. I ran out of room on it there. But there we go. And that's our last page.